Hi there everyone, welcome to the video lecture series on double integration and polar coordinates. I'm Mayur Gohil. In this video lecture I shall be giving you a short introduction on polar coordinates and how to set up a double integral using polar coordinate and the rules of polar coordinate. Okay, so let us see here. Here we have the frame of reference of Cartesian system, which is given as xy plane. Okay, so x-axis and y-axis are the frame of reference that we call, and here any point in Cartesian system can be written as p x comma y, and we can locate that point with the help of the coordinates that we are given, so that is x and y. Now a similar notion is followed in the polar system, but the visual is slightly different. Okay, here you can see the Cartesian system looks like a box all throughout, because it's the way the x-axis and y-axis translate, and that's how the whole system is made. But the polar system looks something like this. Let me give you the visual. It looks more or less like a radar system formulated. Now let me tell you how the whole polar system is formulated, and then we can plot some point also. So if I have the system over here, now this is like, you can see this 0 over here, this is the angle 0. Okay, and here there is a origin over here. Okay, and now any point on the polar system needs it is made up of p r comma theta. So if I want to plot let's say the coordinate for this over here, so the point, let's say I'll call it a, then this point is going to be the radius ar4, right? R4 is the radius, and theta 2 is the angle. So in polar system there are two coordinates. First one is the radius, other one is theta. Now the radius are of different numbers over here. So the circles that you can see there, these are concentric circles centered at origin of with different radii over here, r1, r2, r3, r4, r5. You can have n number of radii over here, and theta I have just taken few for understanding: theta 1, theta 2, theta 3, theta 4, theta 5, here like that. So there are various angles that you can rotate. Okay, now here what is important to note, that radius can become 0, and it is always less than infinity. Okay, so the value of radius is always non-negative, and for theta can take values between 0 to 2 pi. That is what is important. Now we always take theta in positive direction, that is anti-clockwise direction. If we take in clockwise direction, the value of theta will become negative. Okay, so this is the polar system graph. That is how it appears. So if I want to plot, let's say we plot this point over here q, and if I call it as q over here, so the angle like the angle over here is theta 6, and the radius is the r3. So the coordinate for q over here will be r3 comma theta 6. Okay, that's how the point is plotted. Let us go further to understanding what are the relations between the polar system and the Cartesian system. Yeah. Now in Cartesian system we have every point as x comma y, and in polar system every point is of the form r comma theta. Okay, now these two systems are associated with a very good equations that are there that manage them. Let us first see the important condition on radius and theta that I just mentioned here. The first condition is that radius is always non-negative, that is, it is always between 0 and infinity, and theta is always between 0 to 2 pi. Okay, so this is one important thing. Another important relationship between the two, the Cartesian and the polar coordinate systems, are x is equals to r cos theta and y is equals to r sin theta. Now when you try to simplify and get the relationship between the two, so you will get x square plus y square is equals to r square, and theta is equals to tan inverse y by x. These two equations are extremely important for us, so we'll just put a brace bracket and put a star over here so we can refer them again. Now let us see how to set up a double integral for a polar coordinate system. Now we have already seen the double integral of the form double integral over region R f of x comma y dx dy. Now for the sake of convenience I am taking the order dx dy. Here this is equivalent to double integral over region R f of r comma theta r dr d theta. Now observe the changes that are happening. That is, the function has now got converted from f of x comma y and it has become f of r comma theta. Now there is one more term r over here. Now dx dy has gone to dr d theta. It appears so, but now let me tell you the original thing. The originality is that dx dy was the differential in the Cartesian system, that has got changed to r dr d theta. Okay, the function has just become f of r comma theta, and now this r has come extra from when you have changed from one variable from the variable x y, when we moved into r dr d theta, the differential has got one more term r over here. Now what is this r term? Now remember, this is because of the calculus or the mathematics that we are having here in the world of calculus, that whenever you transform the variables from one set of variable to another variable, there is the change of the shape of the figure is going to take place. Okay, the area or the figure may change, so that figure has to be incorporated, that figure changes and the properties have to be incorporated. So one of those reasons is there we calculate Jacobian. Now what is this Jacobian? This Jacobian takes care of the change of the variable, or no component gets lost in the transformation. So dabba x by dabba y over dabba r theta, dabba x comma y over dabba r comma theta. This is the formula for the Jacobian. Now the formula means what? What is the meaning? It is the determinant of what? So the x you take with the variable r, you take the partial derivative with respect to r. For y also you take the partial derivative with respect to r. Okay, in the next row you write the x with and take the partial derivative with respect to theta, and for y you take the partial derivative with respect to theta. How do you get these partial derivatives? You use the equation, the relationships over here, x equals to r cos theta, y equals to r sin theta. Now when you do the partial derivative, you will get your answer as r. Okay, this is Jacobian. You need not worry to calculate the Jacobian all the time. It is very standard in the world of double integration that whenever we convert the variables from Cartesian to the polar coordinate, okay, so dx dy or dy dx, it always gets converted to r dr d theta. This is a standard formula you can treat. The Jacobian always comes out to be r. There is no other answer over here. Okay, so I just showed you the intricate calculation. How does this dy dx gets converted to r dr d theta? Now the arrow that I am referring here, it doesn't mean implies, it means changes to. I request you to read it as changes to. Okay, Now once we are set up with the differential and what is the function, we need to write the limits. Okay, so the limits are written in this format. So the outermost limits of the polar coordinates are always the value for theta. Okay, in most of the cases we have the value of theta coming in the outermost integral, and the innermost integral we always write the value or the limits are always for the radius. Okay, and we always keep the order as r dr d theta in polar coordinates. Okay, let us go further. How to write the limits, how to find the limits for radius and theta. So consider the following figure. Here in this figure I have taken up a region whose curve, or the lower boundary you can see is, it is bounded by the y-axis, this semicircle, and the quarter of the circle. So the quarter of the circle, the equation of the quarter of the circle is r equal to 2. The semicircle is having the equation r equal to 2 cos theta. Okay, now we have to set up the limits, or we have to find the limits for the following double integral. The function we are keeping it general, that is f of r comma theta into r dr d theta. In order to write the limits of the radius, what do we need to do? See here, for radius we from the origin draw a ray passing across the region. Okay, so from the origin draw a ray passing across the region. So like this you draw a ray. Whenever you draw a ray, you have to check the point at which the ray enters the region of the integration will give us the lower limit. So here it has entered at the yellow dot. Okay, so the yellow dot is the lower limit of the radius. So r equal to h1 theta, so some function over here of theta, so that is 2 cos theta. So that 2 cos theta is the lower limit. Okay, now here the point at which the ray exits the region of integration will give us the upper limit, so that is r equal to h2 theta. So here you can see it exits at this blue dot. So at this blue dot the radius equation is r equal to 2, so the upper limit is 2. Okay, yeah. Now let us see how to go for finding theta. For finding theta you have something little bit imaginative here. So move or sweep a ray across the region in the anti-clockwise direction so that the entire region is covered. Now see here, I'll be just supporting this entire statement with the help of the animation, so the whole idea gets clear and you can imagine the whole concept. Here this is the way you have to do. You have to imagine this kind of arm going here. Let me show you again the whole animation. Here this is how the animation works. See, you have to imagine this kind of sweeping of the arm right from the 0-degree angle, because our theta always begins from 0. Okay, wherever it's the whatever be the case, if it is the case of some another kind of region, start from where the region is beginning. Okay, or generally we start from 0-degree. So let me show you once more. This is how you sweep the region. Now when you sweep the region, you can see what happens. The limits for theta, the point or the part at which the ray touches the region first while moving in anti-clockwise direction is the lower limit of theta. So we can see that it started from the 0 degrees, so the lower limit of theta is going to be 0, and the point or a part at which the ray touches the last, okay, while moving in the anti-clockwise direction, that is going to be theta equal to theta 2. So that is going to be the upper limit. So basically here you can see at last it came and halted at the positive direction of y-axis. At that direction the angle is always pi by 2, the 90 degrees, right? So pi by 2 is your answer. So here is the setting up of the limits we are done. So go through the entire theory of this. How did we get it? Here this animation that was there, that is very crucial, because that is where we have to imagine for theta. We will see how to set up more integrals in our further video lectures. Till then, keep solving good amount of mathematics. Thank you for joining in, and please like, share and subscribe with your friends and the students, those whom you find that they will benefit from the following video lecture. Thank you.